Another differential operator that we call the Laplace operator results when we compute the divergence of a gradient vector field. So I've got this gradient field, and I want to find the divergence of it. Well, the divergence is defined as this del operator, which is a differential operator, dot the gradient of f. So when I look at this, this is going to be the partial with respect to x, the partial with respect to y, the partial with respect to z, dot the gradient of f, which is the partial of f with respect to x, the partial of f with respect to y, the partial of f with respect to z. So if I take the dot product of this, what I get is the second partial of f with respect to x plus the second partial of f with respect to y plus the second partial of f with respect to z. Now, this operation is so common, particularly in physics, that we often simply write this as del squared f. Obviously, where we're thinking of del squared as del dot del. Now, del squared is what's commonly referred to as the Laplace operator because of its relation to Laplace's equation. Let's say this. Call this the Laplace equation, which was this. Oops, that's a plus. Yeah, sorry, getting a little sloppy here. Second partial of f with respect to z equals 0. Laplace's equation is right here. It's the solution to this. And that has a very common, or it's used quite a bit in physics. Now, this Laplace operator can also be applied to vector fields. So if I'm going to apply this to a vector field, it would look like this. Now I'm dealing with vector field. That's simply going to be equal to del squared pi plus del squared qj plus del squared rk. Again, this is something that physicists use it quite a bit.